Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.
I have to say, when I first heard about this lecture series, I really couldn't believe that this room would get filled on a Saturday morning. But I came last week for the first time, and can you raise your hand if you were here last week? Okay. So most of you actually come every week. That's impressive. It's a pleasure, especially considering that I've only seen people go to football games over the weekend. So it really is, it's great. So thank you for coming and hearing about physics on a Saturday morning. So today I'm going to have a very basic talk that will touch on string theory only towards the end of the talk. And next week I'm going to have a second lecture where I'll just talk about string theory and applications to cosmology and our understanding of black holes and possibly ways to test string theory. So you might get a little bit bored today, but I hope that you can come back next week because this is really much more exciting. So the basic outline is that I will start from a review of the fundamental building blocks of nature, or at least what we think are the fundamental building blocks of nature so far. And then I will tell you why general relativity doesn't like quantum mechanics. And this is a motivation for the reason why a lot of particle theorists these days are looking at string theory. And as I said, next week we're going to look at applications to research, current research in the field. So there are some very old questions that have fascinated men and even some women for centuries. Although we don't hear about the women. But in fact, last week, I was looking for pictures, good pictures to use for this talk. And I ran across a picture that I have never seen before. So this was a talk given by a professor at Harvard. And he was talking about the Harvard calculators from the 20s, I think. And then it shows a picture of a room filled with women with pieces of paper. So those were the Harvard calculators. I didn't know about it. I mean, I was impressed. So it's remarkable that even then there were women doing math, except we don't really know about it. So the fundamental questions are questions such as what are we made of? And what are the forces that keep us together? And you probably know that a very long time ago, people introduced the ideas that the fundamental units that were making up everything that you could see were earth, air, fire, and water. This was just one of many ideas. And even the concept of the atom dates back to about 400 before Christ, and it's due to Democritus. So these are definitely concepts that have been around for a long time. So the common themes that you find if you look at the development of philosophy, which led to physics, are that people realized that nature seemed to have some order. So the sun was coming up every day. Planets seemed to move around in a certain regular way. There were patterns that they started observing. And so they tried to give rational explanations for the order in nature. And at the same time, they were looking for the basic building blocks of nature. And the atom, which was introduced by Democritus, means precisely something that you cannot divide. So Democritus thought that nature was made of these small objects that he called atoms that you could not divide. Of course, we have made a lot of progress since then. Science has gone really far, and we have found smaller and smaller building blocks. So Einstein, which will make several appearances in my talk, we now understand how we're made of organs and then cells and molecules, and eventually you go down and you find the atom. So if you study chemistry, you spend a lot of time learning about atoms. But if you're a physicist, you learn that atoms are not fundamental. And we now know that the atom itself has structure. So if you look at the atom and you look inside, you will see a bunch of smaller particles moving around. In fact, you'll see the nucleus surrounded by electrons that are orbiting around the nucleus. But if you look inside of the nucleus, you realize that the nucleus also has structure. In fact, it's made of protons and neutrons. And notice that you just went down from something that was about, a millimeter. A millimeter is a thousandth of a meter, so this is 10 times smaller than that. You went down even farther to much, much smaller distances, and you found structure inside of the nucleus. And now you can imagine where this is going. Protons and neutrons also have structure. They're made of quarks, which are represented over here. So if you want to get an idea for sizes, if you look at the size of a quark relative to the size of the atom, that number is very close to the size of an apple compared to the size of the Earth. So quarks are really, really small. And to probe very small distances, we need to increase the energy. So the higher energy you can reach, the more you learn about things that are really small. And so doing this, by probing higher and higher energies, we managed to reduce matter or nature to a very large collection of elementary particles. So this is an example of an accelerator where particles are smashed together. This is the famous ring of the LHC. It's a Large Hadron Collider. This is the most energetic, the best accelerator so far, which is supposed to start running this summer. And notice how big it is. So the diameter is about 5 miles. So this is a huge experiment. It's using the ring of a pre-existing experiment. But this particular experiment, LHC, which we will talk about more next time, and I'm sure you will hear about it in later lectures, is reaching energies that are much higher than what we have done so far. So on Earth, and I want to emphasize on Earth, because next time I'll show you that we can try to use cosmology as a microscope into very small objects. But on Earth, this is the best type of microscope that we have so far. So particle accelerators are what we build to probe small distance physics. And by the way, notice that these are the Alps. So physicists, since they have a pretty miserable life sometimes, like to build things in beautiful places. So this is built near Geneva, and that's a beautiful view of the Alps. Okay, so how do they work? How do these particle accelerators work? The idea is very simple. You take a bunch of particles, you accelerate them to very high speeds, and then you throw them against each other. So this is a picture of an electron colliding with its antimatter partner, the positron, and giving off a bunch of new stuff. And we have diagrams that are very useful to represent this type of processes. So this is just a picture that contains a lot of physics. And the idea is that you would have two particles, I guess you can read it this way, sort of two particles coming towards each other. They interact in some way by exchanging some other particle, and then they proceed. And these are called Feynman diagrams. They were introduced by Feynman. And although they look like a simple picture, they really contain a lot of information. The output that we get from this type of experiments is a lot of information on new physics, and then some very nice pictures. So this, I think, is one of the collisions that gave us the top quark. And this, I can't resist to put it on the slide. It's from a completely different experiment. This is the so-called relativistic heavy ion collider. I can't resist to put it up for two reasons. One is that it's incredibly beautiful. So this is a real collision. There are millions of particles coming out. And the other reason is that I was there when this was taken. This was my first summer as a graduate student, and I was working for one of the experiments involved with this relativistic heavy ion collider, which is on Long Island. Although they knew that I wanted to do theory, so they stuck me in an office for the whole time. But I was very happy about that. So I was in an office doing some calculations, but at the same time, this accelerator was starting up, and it was producing data, and this came out at the time, and it was a big deal. Okay, so we have learned in the past 50 years or so that matter is made of a lot of tiny particles, and there are so many of them that we call it a particle zoo. And this is just a chart that lists some of them. So you have electrons, protons, neutrons. The thing that you should notice is that this chart tells you that some of them are fundamental, some of them are not fundamental. So the natural question to ask is, can you find a fundamental building block in these particles? So if there are so many particles, does it still make sense to ask, is there one that we can call fundamental? And string theory thinks that if you look inside of all these particles, and if you had a very powerful lens, you would see a bunch of vibrating strings. So that's the simple idea, and we'll come back to it later. So what holds all of these particles together? What are the forces that are governing our life? And by the way, this is a little joke for the physicists in the room. So there are 4 known interactions or forces. 2 of them are very familiar. I'm sure you all know that gravity is what's keeping you here in this room, and as well as electromagnetism. So electromagnetism and gravity are very familiar to us from everyday experience. You can see these slides right now because photons are interacting with your eye. Photons are the particles that are responsible for carrying the electromagnetic force. But then there are other forces that you may be less familiar with that you can only see if you look very deep inside the nucleus. So we have the nuclear weak force and the strong force. The strong force is what is keeping protons and neutrons together inside of the nucleus. And the weak force is responsible, for example, for some radioactive decays. But the important feature is that these are really only visible if you look inside of the nucleus. Now, we have a very good description of all the forces that I put on the previous slide, except for gravity. We have a good description for gravity as well, but it's a different type of description. So the so-called standard model of particle physics is a model for the forces that are, right. So this is a cartoon for the forces that I put on the previous slide. Obviously, the guy with the apples on his head is supposed to represent gravity. For some reason, we always associate gravity with falling apples. And that's thanks to Newton's story that apparently Newton was struck by a falling apple, and that's what led to a lot of new physics. I don't think that story is accurate, but in any case, when you see an apple, think gravity. And then there is, this guy is electromagnetism. You can see a lightning and a magnet. And then obviously this guy is weak and this guy is strong. So these are the 2 nuclear forces that I told you before. The guy who cannot lift a lot of weight is the weak force. So 3 of them, these 3, fit very well inside of the framework of the standard model, this model that can describe very accurately everything except for gravity. But we already know that the standard model is not a complete theory. It turns out that although it works very well, there are some questions that are not answered inside of the standard model. So for example, we still don't know whether quarks, those particles that I told you about earlier that are inside of protons and neutrons, we don't know whether they're fundamental or not. We seem to think right now that they are because we cannot see anything inside of them. But it's not clear whether they are fundamental or not. The same story for the electron. Then the way in which particles get their mass, the mechanism by which particles become heavy, is not well understood within the standard model. And then there are big questions such as dark matter, and I'll come back to this next time, and Elena Razia, who's going to talk to you after spring break, is going to say a lot about dark matter, probably. So dark matter is a large component of the matter in our universe. It's about 21%, but we don't understand what it's made of. So this is a big theoretical question in physics. And then there's the question about gravity. Why is gravity different from the other forces? Why doesn't it fit inside of this framework? So this should tell you that we need a theory that is more fundamental. We need a theory that goes beyond the standard model and that can answer all the questions that are still puzzles. And some of these questions will hopefully be answered by this experiment that I was telling you about, the LHC, this big particle accelerator that is going to start working in the summer. Now we have evidence that these forces, the four forces, are just different aspects of one single force, of the same interaction. In fact, what we know, so this is a picture that tells you, so notice that this is gravity, this is a weak force, this is electromagnetism, and a strong force. And this is a picture of their behavior as energy increases. So if you go up on this graph, the energy is increasing. And you don't have to pay a lot of attention to these numbers. But the point is that as energy goes up, you are looking at farther and farther back in time. So today, right when we're right here, we see four distinct forces. So to us, gravity and electromagnetism and the nuclear forces, they all look like they're different, they're distinct. But as you go to higher energies, notice that they start merging together. So for example, the weak force and the electromagnetic force merge at about this energy. And if you go even farther up in energy, they merge with a strong force. And if you go even farther up, we expect that gravity will merge with all of them. So at very, very high energies, or alternatively, very early in the evolution of the universe, a long time ago, we expect that all these forces should become just one force. And we believe that string theory is currently the best theory that does the job of unifying all the forces into one. Of course, it's just a candidate, but we think that it's the best candidate we have. So until somebody gives us a better theory, this is where most of the particle theorists are spending their time doing. So what do I mean when I say that these forces will become unified into a single force? So one somewhat simple way to think about it is to think about electricity and magnetism. These two phenomena are connected to each other. You may know that if you take an electric charge and you make it move, it's going to give off a magnetic field. So moving electric charges cause magnetic fields. On the other hand, if you change a magnetic field, you create an electric current. So these electric phenomena and magnetic phenomena seem to be related to each other. And if you look at a picture of the electric field lines, so these are supposed to represent the attraction between a positive charge and a negative charge. And you compare that to the field lines in a magnet. So this is a magnet with the North Pole and the South Pole. You see that they look very similar. And this is not an accident. It's due to the fact that these two forces are really the same force. They're just different aspects of the same force. This is something that we have known since Maxwell, so for a long time. So this is one example of unification. You have two phenomena that look different, but they're really different aspects of the same thing. That's what I mean when I say unified. So why is gravity special? Why doesn't gravity like to fall into the same bin as the other three forces? Well, so Einstein is coming back over and over during my talk. So you might blame him. Maybe it's his fault. Maybe he didn't do a good enough job. But it turns out that he did a great job. In fact, we have a model that works very well that describes gravity. It's called general relativity. It's due to Einstein at the beginning of last century. It's a classical theory of gravity, and I will tell you what I mean by that in a few minutes. It works well everywhere on this planet and on larger scales of the size of the universe. So it works very well if you're studying falling apples, if you're studying motion of planets, rotations of galaxies, satellites, even GPS systems work on general relativity. If you don't take into account general relativity, a GPS system will give you the wrong answer. So this is a theory that works incredibly well on large scales. On the other hand, I told you that we have an equally good working model for particle physics, the famous Standard Model. This, on the other hand, is based on quantum mechanics, which is very, very different from classical theories. And I'm going to come back to it in the next slide. And quantum mechanics, or this working model for particle physics, describes very well things that are very small. So protons, neutrons, elementary particles. So why is there a conflict between, and this is a shorthand, quantum mechanics and general relativity? They're incompatible with each other, but why? So there are deep reasons that are a little bit technical, but an easy way to understand is that general relativity works well on large scales. It's a classical theory that can predict things very well. It's deterministic. On the other hand, quantum mechanics works very well on small scales, but it's probabilistic. That means that it can only tell you probabilities of certain events happening. And this is due to the famous uncertainty principle, which is the idea that, for example, if I want to know if I am a very small particle and you want to know my position and my velocity at the same time, you will not be able to do that. You will only be able to tell my position if you want to know my position very accurately, then you will not be able to tell how fast I'm moving. There is a certain uncertainty associated with measurements. And this is at the origin of the fact that quantum mechanics can only tell you probabilities. There's nothing wrong with that. It's a theory that works very well. It describes how semiconductors work. It's extremely powerful, but it's very different from a classical deterministic theory, where you know that if I give you enough information, you will be able to tell that I'm here and that I'm not moving very fast. So classical physics can give you precise answers, not just probabilities. So the assumptions of these two different theories are very, very different. So they work well in regimes that are opposite. One is on large scales, the other one on small scales. And of course, there's this difference between classical and quantum mechanical. So you might wonder, or you might ask, is a theory of quantum gravity, so a theory that includes quantum mechanics and gravity, just a matter of taste? Is it that these string theorists or particle physicists are just interested in finding beautiful equations, but they don't really have good motivations for them? And it turns out that it's not just a matter of taste. So why should we worry about the fact that these forces don't all behave the same way? So after all, we do have these beautiful models that work very well in their respective regimes. But there are places where gravitational effects and quantum mechanical effects are equally important. And if they're equally important, you need a theory that can describe both of them at the same time. So examples of places where the two theories are equally important are black holes, which we know exist, as you heard last week from Gus. For example, you know that at the center of our own galaxy there is a black hole. So black holes are places, are sort of objects that look like this, and we'll come back to them in a minute, where gravitational effects are very, very strong, but quantum mechanical effects are also strong. And the very early universe, around the time of the Big Bang, is another place where those two theories, those two effects are equally important. So what do these examples have in common? So they involve very small sizes, and the curvature, the amount of bending of the space, is very high. And we're going to have a demo in a minute that explains to you what we mean by curvature. So when the universe was just born, it was very small and very hot. And because it was small, quantum mechanics was relevant there. And black holes are objects that have very high curvature. So imagine a sheet that's bent, and the amount of bending is extremely high. And places that have very high curvature are places where gravitational effects are very important. Okay. So I hope I've convinced you that the reason why general relativity and quantum mechanics don't like each other is because they're based on very different ideas, and they make different assumptions on how the universe works. Now, it turns out that one of the things that Einstein taught us with the development of general relativity is that if you take a very heavy object and you sit it inside of the universe, or what we call space if you sit it inside of space, then it causes the space around it to bend. So notice this is supposed to be a picture showing that as the Earth is moving, space around it is bent a little bit. On the other hand, once the space is bent, any matter that you have around, any particles that are moving around, and even light, will move accordingly and will have to follow the curvature of the space. And this is a very important idea that we learned thanks to Einstein. And so in this sense, the geometry is changing in time. As the mass is moving, it is changing the space around it. It is bending it more and more. And as the geometry is changing, any particles around will also move in different ways. But theories that describe elementary particles like protons and neutrons are usually based on the assumption that the space on which things move is fixed. It's not changing in time. It's just a fixed background. So these are very, very different ideas. And now I would like to show you a demo that demonstrates the idea of the curvature of space. Notice that you have this rubber sheet, and it can bend a little bit. And we're going to put a very heavy mass on top of it.
So the rubber sheet represents two-dimensional space. And if I put something very massive on this two-dimensional space, it's going to bend it. And we're going to see the masses move towards each other. So here's a very massive object, like a black hole at the center of the galaxy.
Maybe we should run it again.
Run it again.
Also, for those of you who are sitting nearby, notice that the bottom is also bending. Notice that there is curvature here. This is not flat. So this is what's happening in space. A very heavy object is making space bend. And also time, by the way. So it's space-time that's bending. Of course, here we can't do this with time. But in real life, out there in the universe, time is also bending. Okay, so Einstein likes demos. This is a beautiful animation. There's a website where you can add anything you want to the blackboard and then save the picture. It's great. So I think you can Google Einstein and dynamical blackboard, and it will take you there. Okay, so we saw that very massive objects can change the curvature of the space. They can make it bend differently. So now imagine putting a really, really heavy object on that thing. It's possible that if you make it incredibly heavy, that it will break the rubber band. So this is how black holes work. A black hole is a very massive object. It's so massive that it causes space-time to bend until the curvature becomes infinite. So it becomes incredibly large. And it's called a black hole because, of course, I'm assuming you know that gravity is attractive. So gravity, this heavy object, will attract things around it. And it's so massive that it even attracts light. So the light rays go in and it cannot escape. So that's why it's called black. It's called black because it doesn't emit any light. Well, because it's sucking in even light. So black holes are pretty complicated systems, but the main idea is that they have a point inside where the curvature is so high that we call it a singular point. It's a singularity, a point of infinite curvature. And then they have a region after which, if you're moving this way and you pass this event horizon, you cannot escape the black hole anymore. So the horizon is the last place where you are allowed to turn around without being sucked in. So it turns out that general relativity, the theory that Einstein developed, doesn't do very well with singularities. It breaks down. So anytime that you see a singularity in general relativity, it's simply telling you that the theory is not good enough to describe it. It's not telling you that there's some fundamental problem with this object. It's just saying the theory you're using is not good enough. So you should switch to a different theory. And the reason why the theory is breaking down is because this little tip is so small that quantum mechanical effects are becoming important. So to deal with objects like that, to describe them properly, you need a theory of quantum gravity, theory that unifies quantum mechanics with gravity, or that can describe both of them at the same time. So far, I've told you that gravity is special. Classical gravity, meaning general relativity, is not good enough for describing certain places or certain times. It's not good with dealing with singularities and the very, very early universe. So we need some more fundamental theory of quantum gravity. And this is a very challenging program. These are very difficult problems. So why do we want to look at string theory? Why do we want to look at strings? The normal advertisement that you see is that string theory incorporates naturally general relativity and quantum mechanics. And I'll show you later why it does so. So it's a leading candidate for a consistent theory of quantum gravity. It's probably the best one we have so far. The idea behind string theory is very, very simple. If you look deep inside these particles, you would see a little string, something like that. So the fundamental unit that we have been looking for would be a tiny vibrating string. This would be the fundamental entity that makes up everything. But how small is a string, you might ask? I mean, can we ever see this? What's the natural size of a string? It turns out they're incredibly small. They're about 10 to the minus 34 meters. This corresponds, if you translate it into energies, to energies that are about 10 to the 18 times the mass of the proton. So this may not mean much to you, but, okay, sorry, let me back up. So if you average the amount of food that you would eat in 1 year, so if you count the calories and add them up, you'll get an energy that's about this one. And I have to tell you, this started a very funny conversation. So I read somewhere that this is also the energy that it takes to send a moon, no, not a moon, send a cow to the moon. So I didn't understand exactly what they meant by sending a cow to the moon, also because the cow would disintegrate when it's leaving the atmosphere. So with a bunch of physicists, when I brought this up, we spent about an hour trying to figure out what it meant to send a cow to the moon, and then we realized that it would be easier to leave the cow out of the picture and talk about calories that you eat in 1 year. So we could check this calculation, it works out, but I still don't know how to check a cow to the moon. Although I did it, we did it in a couple of different ways. Okay, so how small is this number? So remember that earlier I had a picture of I told you, I think, that quarks, the size of a quark to the size of the atom is like an apple to the Earth. So if you compare the numbers, the size of a string to the size of a quark is like an atom to the Earth. So strings are incredibly small. So this is an example of what is called an open string. It turns out that in string theory, we also have closed strings. They look like little loops. Can we produce them in a lab? The answer is no, because the energy that you would need to produce it is way too high. The size that you would need to probe is very, very small. So this is the famous LHC. This is another beautiful picture, but the Alps are gone. And this will reach about, I think, 10,000 GeV. So the GeV is the natural mass of a proton. So between 1,000 and 10,000, I think. The energy that you would need to see strings is much, much higher than that. So that's the reason why you cannot produce it directly in the lab. So testing string theory directly is very difficult. It's not impossible because producing the string is impossible, but testing them, you could manage to devise ways to test them. And I will tell you next week a little bit about cosmology. It turns out that cosmology is gives you pictures into the very early universe where energies were very high. So cosmology might be a good way to try. So indirect testing is where the efforts are concentrated. And what I mean by indirect is that you look for ingredients of string theory and you ask, can those ingredients leave footprints on things that we can actually measure at places like LHC? Can I see some signatures of this very high energy physics at lower energies? And a lot of people are working on this. Okay, so how do we recover the particles that we actually observe from a string? So for those of you who took general physics at some point, you probably remember studying the vibrations of a string that's attached to two ends. So if you take a guitar and you plug a string, you know that you can get different notes out of it. You can get different frequencies. So the string would behave, this very small fundamental string would behave in a similar way. It can vibrate in different ways. And the different vibrations mode would correspond to the different particles. So there is a way to associate the frequency, the vibration mode of a string to the particles that we observe. So this is an analogy. It's not quite that simple. There are a lot of technical details involved, but it gives you the right idea. Right, so the analogy is with the standing waves on a string. And it's time for another demo. For those of you who saw Lost in Translation, this will mean something. So we're going to reproduce standing waves on a glass. So what they have there is a glass that is going to start vibrating. It's attached to a speaker. So as you can see, it's tapping the glass. And this ring is the rim of the glass. Oh, and close your ears. It's going to get loud.
So we're driving a frequency that is exactly the same frequency as the cup. You can hear me ping the cup. So we're driving it with a sound wave. And what we want to look at is the rim of the cup. I'm going to put on earphones. If it gets too loud, go ahead and plug your ears. So you can all see the rim of the cup moving in and out. I'm going to go ahead and increase the volume. Okay, ready?
Okay, it's very important that you don't get away from this with the idea that strings will break like that, okay? That wasn't the point of the demo, but the point was to see the vibration of the glass. So that's an example of a standing wave on the glass. Okay, so let's go back to string theory. So why is it a theory of gravity? So first of all, it includes quantum mechanics because strings are very small. And when things are very small, that's where quantum mechanics comes in and matters a lot. So again, this is a picture roughly of what you just saw. This is a closed string vibrating. So this would be the vibrations of a closed string, and this would be the vibrations of an open string. So the glass you just saw is some sort of, it's basically like that. It's a standing wave on a closed string, a circle. So it turns out, as I told you before, that each mode of vibration can be translated into a different particle, at least into objects that have different properties, and down the line they can be identified with different particles. And this is a very, very technical process, but that's the main idea. So one of these is the so-called graviton. One of the vibration modes of a closed string is the graviton. So what is the graviton? The graviton is just a particle that we think, the object or particle we think is responsible for carrying the gravitational force, in the same way that photons are responsible for carrying the electromagnetic force. They're carriers of the electromagnetic field. So it's in this sense that we say string theory naturally contains gravity, because one of these vibrations is precisely the carrier of the gravitational force. By the way, we have not seen gravitons yet. This is a very big deal. When they will be discovered, it will be great. We expect that they exist, but we haven't seen them yet. And our experiments whose sole purpose is to measure them. So strings can also interact. Remember earlier I told you that in particle accelerators we smash particles together, and then these particles interact with each other. So they meet, they give off a new particle, and then that particle can decay into other particles. So this is a type of interaction between elementary particles. Strings interact in similar ways. So now this would be some circular string comes in, meets another one, they join, and then they can split, decay into other strings. By the way, this is called a Pence diagram.
Yeah.
Because if you slice it here, so forget about, say, this side, they look like pants. So that's a Pence diagram. Notice that these particles meet at a point, because particles are point-like, they're very small. But strings are no longer point-like, they're big objects, and so they don't meet at a point, they meet on this surface. It turns out that this reason, this simple reason, through very technical details, is related to the problem of why we cannot unify gravity with the other forces. It's the fact that the string doesn't have this point-like structure that helps and allows gravity to be incorporated with quantum mechanics. So it's a very subtle idea, but you can trace it back to the fact that these point particles are really meeting at a point. They're point-like, and the string is an extended object. So when we look around us, we see 3 spatial dimensions, and then we like to call time also dimensions. So we see 4 dimensions. It turns out, and I'm going to leave this animation on here because it's so beautiful. It turns out that strings don't like to live in 4 dimensions. They like to live in 10. So that's a problem because we don't see 10. But one way in which you can get around the problem is by saying that the other 6 dimensions that you don't see are really small. They're so small that we cannot detect them yet. And they could look like these. So this plane is supposed to represent the 4 dimensions we live in. And then you could have these attached extra dimensions everywhere, these small, compact, very tiny dimensions that we don't see just because of their size. And they can have very complicated shapes like these guys and very complicated structure. They need to be small enough that we cannot see them. So these are what are called compact dimensions or extra dimensions. It turns out that string theory doesn't just contain strings. There are other ingredients that look like membranes. They look like sheets of paper. Sometimes they're called branes, sometimes membranes. They have slightly different properties. And so you could have a universe made of these membranes with strings that can attach to them, and then other strings floating around that are not touching the membrane. So it turns out that these open strings can attach the membrane. The closed strings don't. So we think that if you look deep inside the structure, you would find both of these types of objects. You would find membranes with complicated strings that are stretching between them, and then closed strings floating around. So how can you use these ideas that are coming from string theory? It turns out, and I'm going to go into much more detail next time, that strings and membranes have given us a lot of insight into the relationship between gravity and quantum mechanics. In the past 10 years especially, we have learned a lot about why gravity and quantum mechanics can talk to each other. We also have learned a lot about black holes. Black holes are objects that have caused a lot of problems for a long time. There were a lot of important deep questions that we were not able to understand related to black holes. For example, we know that black holes have a temperature, and if an object has a temperature, there's some entropy associated with it. And string theory has succeeded in reproducing the entropy of black holes just by using these membranes that I was telling you about. This is a very remarkable result. It turns out that string theory has also succeeded in explaining some singularities. These were the places where general relativity was breaking down. And you can use these membranes and combinations of strings also to model universes. So you can build models for universes, and then you can test them. You can say which one of these is closer to the standard model, which one of these is reproducing the early evolution of the universe that we understand from cosmological observations. And this goes under the name of model building. So a lot of people are spending a lot of time building better and better models of the universe. There is also a possibility that these extra dimensions that I was telling you about can be large. They don't necessarily have to be small. So people have introduced the idea that we, meaning our universe, what we see, what we observe as our universe, may be living on one of these membranes. And this membrane is sitting into a much bigger space that would have to be 10-dimensional. And it's also possible that somewhere else there's another membrane where parallel universes may be. So this is, of course, just a model. We don't know whether it's true or not, but there are a lot of people who are working on models of this type. So in this case, we don't need small extra dimensions. See, if we live on this membrane of this universe, we don't see the other dimensions just because they're sort of perpendicular to us and because of other technical problems. But this is an alternative to thinking that the additional dimensions have to be small. So for example, there are people who claim that maybe the Big Bang was caused by these two membranes approaching each other, smashing into each other, and the place where they collided is what we call the Big Bang. And then after the collision, they started moving apart from each other, and that's what we observe as being the acceleration, inflation or the acceleration of the universe. Again, these are only models, but you should be aware of them. So I think I'm doing pretty well on time, so this is close to the end of my talk. So very often I get the question, so what do you do? So people think that I sit in a lab and that, they think of me as some biologist who sits in a lab and don't understand how this goes together with all the ideas that I've been telling you about. So most of my time I use pen, paper, computer. I think that's what most string theorists do. Actually, all of them, nobody works in a lab. We wish we could, but we don't. There are no labs yet to test string theory. So what we really do is try to understand the properties of strings and membranes. And by understanding their properties, we are understanding more and more about quantum gravity, which is what we're ultimately interested in. And the goal of what we do is to build a universe out of the strings and membranes that looks like ours. And as I will tell you more about next week, this is very difficult. But that's the ultimate goal. We want to describe the universe that we live in. We want to describe what happened at the very early stages of the evolution of the universe, right after the Big Bang. And we're hoping that string theory is what is going to do the job. So this is the end of the first part of my talk. I hope I have convinced you that we need a more fundamental theory. You learned some string theory basics, and then next week I'm going to tell you a little bit about the current research in the field, specifically with applications to early universe cosmology, black holes, better understanding of quantum gravity, and possibilities of how people are trying to see if you can test string theory. So please come back next Saturday, and thank you for coming.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.